All right, so now we're going to talk about some experimental evidence. So this is, all right, so as I said the other time on the last video, we don't have any missiles or rockets or airplanes or anything like that that can travel even anywhere near the speed of light. So how are you going to do experiments? Well, at a particle accelerator, this is Fermilab outside Chicago, the protons are accelerated here to nearly the speed of light. So these particle accelerators are great places to do experiments with relativity. All right, so here we go. Okay, so the first experiment I want to talk about has to do with a muon. So a muon is a tiny, tiny subatomic particle. And it's unstable. That means it doesn't live very long. And so the average lifetime for a muon at rest, that's important, is 2.2 microseconds. 2.2 times 10 minus 6 seconds. So way back in the late 50s, some physicists from Harvard and MIT, they did an experiment. And the experiment was really for their classes. They made a video of it, and it's very famous. Okay, so what they did, they went to the top of Mount Washington in New Hampshire. And they set up a detector here. And then they set up a detector at sea level. And they wanted to see how many muons they would detect. Okay, so and these muons come from cosmic rays. Don't worry about that. So the muons travel at 0.994 c, so almost the speed of light. Okay, so at the top of the mountain, they counted 568 muons every hour. Now, again, the lifetime is 2.2 microseconds. Okay, so distance equals speed times time. So if you put in the speed, which is 0.99 whatever it was, 0.994 c, and you put in the time, which is 2.2 microseconds, most of the muons should have decayed by the time they reach sea level. Now, what do I say most for? Well, remember, this lifetime here, hold on. Okay, this is an average. So, just like anything, right? You can have some that live just a little bit longer. You can have some that live a little bit less, right? So this is an average. So anyway, so you do all the math, and you expect, based on this and the speed they're going and the average lifetime, you expect to get 27 per hour at sea level. So that's what Isaac Newton would predict, or Galileo. They did the experiment, and they actually observed 412 muons per hour. Now, if this were 26, 28, whoopee, right? But 412? I mean, that's way different from 27. So how do you explain it? Well, let's see now. Who measures the proper time? Well, first of all, what are the events? I mean, if you're going to do a relativity problem, it's always a good idea to figure out what are the events. So what are the events? The event, what are the events? Leave the top of the mountain and then arrive at sea level. So those are the two events. Now, who or what is there at, who, how do you say this? What object is at the same location for both of these? Well, the muon, right? The muon. The muon starts out at the top and he gets to the bottom, right? Okay, but all right, so who measures the dilated time? Well, the experimenters, right? The experimenters see the muon there and then there, so they're at different locations, Okay, so the proper time is measured by the muon, and the dilated time is measured by the physicist. Okay, well, so the proper time, Yeah, I mean, think about it. The muon is traveling down traveling down. According to the muon's at rest, right? I mean, that makes sense, right? So the proper time is 2.2 microseconds. But what did we learn? According to the physicists, the lifetime of the muon will be longer, right? Here's the equation. The dilated time equals gamma delta t. Well, as you start doing these homework problems, you're going to realize that you always have to calculate gamma, or almost always. You got to calculate gamma. So gamma is 1 over square root of 1 minus beta squared. Beta is 0.994, so you square it, you do all your math, you get 9.14. 9.14! Okay, so the dilated time is 9.14 times the 2.2 microseconds, so it's 20.1 microseconds. So stop, make sure you understand what we're saying. The muon thinks it lives only 2.2 microseconds. That's the proper time, right? We, the experimenters, we measure the lifetime of the muon to be 20.1 microseconds, right? Remember, Mort and Zelma, or whatever her name was, right? She says 1 second. Mort says, no, longer than 1 second, okay? So the physicists measure the lifetime to be 20.1. Well, come on. That's like almost 10 times longer than this, right? Well, according to this then, if the time is almost 10 times longer, that means they're going to be able to travel 10 times further, right? Okay, so that explains why so many survived until sea level, because according to us, according to our reference frame, they actually live 20.1 microseconds and not 2.2 microseconds. So these numbers perfectly agree with the predictions from relativity. So that's pretty cool. Okay, here's another experiment. This was done in 1976. So this was an experiment done in Geneva, Switzerland, at that particle accelerator there. So this time they got the muons go even faster, 0.9994 C. And then they measured their lifetime, and they lived 30 times this average lifetime at rest. And it completely agrees with the prediction from relativity. Completely agrees. All right, now here's really a cool experiment. So oftentimes I tell people about the muons, and they kind of say, yeah, Brother Weber, hoo-hoo, muons, hoo-hoo, what are these crazy things? Can't even see them, right? Okay, so in 1977, some physicists did an experiment with atomic clocks. So they had 2 atomic clocks. Atomic clocks are the most precise and accurate clocks on the planet. So what they did, they took one clock and they put it on the Earth, kept it at rest. They put the other one in an airplane and flew it around. Now, according to relativity, the time should differ. And then they switched clocks, and repeated the experiment, to make sure that, you assume the clocks are identical, but just to test it, you switch clocks and repeat the experiment. So in 77, the first time they did it, there was a time difference as predicted by relativity, and the time difference agreed to relativity within 10%. That's not bad for the first time you do an experiment. Then they beefed up the experiment and did it the next year, and the time difference agreed with relativity to within 1%. So that's impressive, right? That's super impressive. Okay, last but not least, the GPS, the Global Positioning System. The Global Positioning System would not work if the people who programmed it did not include the relativistic equations. So this is from a textbook. Let me just read it. If the relativistic effects of time dilation and the gravitational effects of the present chapter, we didn't talk about that, were not properly taken into account, the GPS system would fail after only a fraction of an hour. Okay? So the fact that the GPS system works and you know, it's used all over the world, right, in business and banking and all of science, all sorts of things, that's evidence that relativity works. Because if they didn't, again, if they didn't use the relativistic equations, it wouldn't work. All right, so I think that's pretty good evidence, but I want to talk about one more piece of evidence, because I used to work there, so I'm kind of excited about this. Okay, so let's say we want to do some muon experiments at Fermilab. Okay, so you got to get, I mean, Fermilab is a proton machine, so it accelerates protons, also antiprotons. But we want to get muons. Well, how do you get muons? I mean, you can't just call up Sears and say, I want some muons, you know. You're going to make them, okay? So you have to make the muons. So how do you do that? Well, this is how they do it at Fermilab. So they have the proton beam from the accelerator, and it smashes into a target, usually like some kind of a thin film. And so the protons smash into the target, and what's produced are pions and other stuff, which we don't care about. Okay, pions are unstable. That means they don't live very long. So they decay into the muons plus other neutrino. I don't care about that, all right? So it's kind of a two-step process, right? First you make the pions, then you wait for the pions to decay, and then finally you get your muons. Okay, now let's look at the lifetimes. So the pion doesn't live very long, does it? So these are average lifetimes at rest. So average lifetime for pion, 2.6 times 10 minus 8 seconds, pretty short, right? And the muon, we already talked about, 2.2 times 10 minus 6 seconds. Okay, so if you're going to build an experiment, you got to be really, really careful where you put your detectors. Because, you know, you don't want to detect pions, you want to detect muons, right? So you got to be careful, you know? All right, so let's see. So here's the proton, smashes into the target. This is not the scale, by the way. So then the pions are created, and they don't travel very far because they don't live very long, right? And then the muons are created, and they live like much longer, well, 100 times longer, or whatever, than this, okay? So all I'm saying is you got to make sure that you put your detector where you have muons, you know, not pions, right? Okay, so you got to do some calculations, you know? All right, so let's see. So how far does a pion go before it decays? The average pion, according to Isaac Newton. So x equals v delta t. So you put in the velocity, which is close to the speed of light, and then you put how long it lives, and then 7.8 meters, okay? 7.8 meters. Well, okay, we're assuming that this goes at 0.999999 times the speed of light, which is accurate, okay? So you put that in, you put the lifetime in at 7.8 meters. Okay, so what does that mean? It means that, you know, you can put your muon detector anywhere here, right? Because after 7.8 meters, you'll get muons, according to Isaac Newton anyway. However, Isaac Newton's wrong, right? We've got to listen to what Einstein says, okay? So this is the proper time, right? What we want to calculate, or what we want to concern ourselves with, is the dilated time, the longer time, you know, the longer time. Okay, so, oh yeah, by the way, okay, hold it, sorry. Okay, so according to Isaac Newton, you know, we would put the, yeah, if you're going to do an experiment, you've got to build a just big, giant detector, which takes a building. And so, according to Isaac Newton, we would build our, you know, multi-million-dollar building right there. Okay? Wow, great. However, come on, this is the proper time. We've got to use the dilated time, right? Here's the equation. The dilated time equals gamma times the proper time. And so using the speed of the pion, you calculate gamma, then you multiply by the proper time, and you get this, okay? So, I'm sorry, yeah, all right, so in other words, according to the physicist, the pion doesn't decay after 2.6 times 10 minus 8 seconds. It decays after 5.7 times 10 minus 7 seconds, which is a lot longer, right? So if it lives a lot longer, that means it can travel a lot longer, right? So here's the relativistic distance. So, you know, x equals 0.999c times this nu delta t. and you get 174 meters. 174 meters.
The circulation test will be closing in 5 minutes. If you wish to check out any library books or DVD, please do so now. Please return all books, videos, and other materials at this time. Mahalo.
Okay, so again, if you didn't use relativity, you'd build your building here, where most, okay? However, if you use relativity, you realize, my gosh, I'm going to get pions all the way up to here. So you have to build your building there. And guess where they built it? There, obviously, right? So, I mean, that's pretty good evidence, right? That's pretty good evidence. And, I mean, you know, these buildings cost tens of millions of dollars in these detectors and all that. And so, you know, you can't make a dumb mistake. You know, you got to use relativity to figure out where the muons actually are. Okay? So I think that's pretty good evidence. All right, something new. Let's talk about a light year. Now, just, you know, when you read that, you say light year. Well, you think it's a unit of time, right? I mean, it says year, you know. Well, it's not. It's actually a distance. Sorry about that. So a light year is the distance light travels in 1 year. It's too bad they call it a light year. Oh, well. Anyway, so light year is distance. You've got to remember that. Now, so here, this is the nearest star, you know, not including the sun, right? So the distance from Earth to Proxima Centauri, the next nearest star, well, that's what it is in kilometers. Well, I mean, good golly, that's a ridiculous number, right? So astronomers don't use kilometers because it's ridiculous, too many zeros. I mean, your eyes go blurry, you know? And so basically it's about 4.24 light years. Here's the conversion. I don't think it's worth knowing. You can calculate it. You can just figure it out yourself, you know, but it's not really worth it. How could you calculate it? You know, distance equals speed times time, right? So you put speed of light and you put a year in seconds. Bingo, you get the conversion. But it's kind of a waste of time. All right. So what does this mean? What it means is it takes light 4.24 years to travel from the star to us. What does that mean? Well, that means when you look at the star, you're seeing the light that left the star 4.24 years ago. So you're seeing, so you're looking in the past, right? You're looking 4.24 years in the past. Kind of cool, right? Okay, so for all you know, the star could have vanished, right? Because all you're seeing is what it looked like 4 years ago. Okay, now let's work with this. I want to show you why we care about light years. Okay, so distance equals speed times time, right? Okay, so therefore velocity equals distance over time. No kidding, all right? Okay, now let's put c for this velocity. So c, you know, same thing, right? Distance over time. Okay, now what we want to do is we want to say the distance is 1 light year. Okay, well, what's the time? In other words, how long does it take to travel a light year? A year. So 1 year. All right? Okay, so c, the speed of light, is 1 light year divided by 1 year. That should make pretty good sense, right? Because the distance that light travels in 1 year is a light year. So that's, okay, all right? But look we don't have to just use light year over year. We can say 1 light hour over 1 hour. We can say 1 light month over 1 month. Whatever we want, you know? I mean, okay? Whatever you like to do, you can do that. All right, so we're going to use this when we do a problem right now. So okay, so c equals 1 light year per year. And again, that should make totally sense, right? Because just multiply it. 1 light year equals c times 1 year. Well, no kidding, right? Speed of light times a year is a distance, which is a light year, which is a distance light travels in a year. So, you know, okay. So it makes sense. All right, let's do a problem. And I'm going to do a bunch of problems, and I want you to understand the method, because I mean, the method works for the great majority of these problems. Okay, this is cool. Okay, in 1998, using the Keck telescope, which is on the Big Island, scientists discovered some previously undetected young stars that are only 150 light years from the Earth. That is only, by the way. Okay, 150 light years from the Earth. Suppose a space probe is flown to one of these stars at a speed of 0.98 c. The battery that powers the communication system can only last for 40 years. Will the battery be good when the space probe reaches the star? Well, what would Isaac Newton say? Of course not. I mean, come on. Going at the speed of light, it's going to take you 150 years to get there. Well, that's close to the speed of light, so it's going to take them a little bit longer than 150 years. But the battery only lives for 40 years, so it's going to be totally dead, right? Well, that's what Newton would say. Now, we don't care about what Newton would say, because he was wrong, right? We got to care what Einstein says. So this is generally a good pattern or a good method to use, okay? All right, so number one, what are the two reference frames? Well, you know, there's the probe, and there's Earth. Okay, number two, what are the events? Well, you leave the Earth and you arrive at the stars, right? So leave Earth and arrive at the star, or stars, whatever, okay? All right, now these are the crucial questions. Proper time, dilated time, all right? Who or what measures the proper time? Well, remember, here's the probe, right? Here's the probe on the Earth. So according to the probe, the Earth is right next door, right next to him. Then the probe goes to the star, and according to the probe, the star is right next to him, right? So the probe measures proper time. So 3, probe measures proper time. And us, right, on the Earth, I mean, you know, we see the probe right here on the Earth, and then we see it way over there by the star. So it's at a different location, right? So the people on Earth, us, I'll just say us, we measure the dilated time, which equals gamma delta tau, right? Okay, so calculate delta t. Right? Calculate delta t. That's what we would think, yeah? That's what we would think. Delta t. Okay, so 4. So what's delta t? You know, well, how long does it take? Okay, so, you know, distance equals speed times time. Therefore, time equals distance over speed, right? Okay, I put, sorry, v, gosh. All right, now we're going to be clever. All right, we're going to be clever. What's the distance? 150 light years. What's the velocity? 0.98 c. But what's c? I mean, I don't like the units for here. Do you like the units for here? No. Light year per c, bad, bad, bad. But c is a light year per year. Yeah? So what's going to cancel? So the light year is going to cancel, and we're going to get the unit of years, which is kind of what we want, right? See, that's incredibly useful. Okay, so 150 over 0.98 is 153. Okay, so according to us, you know, or Isaac Newton for that matter, it's going to take 153 years to get that probe to the star. Wow! What? Okay. But what we want to know is what what the probe says, right?
The library is now in the process of closing. Please take all your personal items with you as you leave. Mahalo and have a good night.
Okay, so this is the formula. So what we want to calculate is the proper time, right? We want to know how long the probe thinks it's going to last, you know? So we got to calculate gamma. You always have to calculate gamma. So let's calculate gamma. All right, so gamma is 1 minus beta squared, negative 1/2. So it's 1 minus 0.98 squared, negative 1/2. So I promise you that's 5. 5. Okay? So therefore, delta tau is delta t over gamma, right? And that's 153 years over 5, and that's 30.6 years. So, according to the battery, remember, it can last for 40 years. The battery thinks it's only going to take 30.6 years to go from the Earth to the star. So by golly, will the battery still be good when the probe reaches the star? Yes! All right, so you see how incredible relativity is, right? Because nobody in their right mind would think it's, in Newton's time, would think it would last. But in fact, it does last. Okay, let's quit. Because I don't want to compete